Mr. Mustafa,
Yes.
were you going to provide a PowerPoint for today?
No, we're gonna use Texas Instrument, resources for that. So
Oh.
as I said, they have. I will share my screen right now. So they have a course for this kit, okay, and this course, have lectures, videos, and everything you want. So we're gonna use for this particular lecture, we're gonna use one of their files. Okay, you see my screen, right?
Yes, we can see it.
Okay, so let's start this. Okay, so this is basically module 12 in that course of TI. Okay, it's basically talking about the physics of motors. So we're gonna cover the physics. I will not ask about for the physics, but if you are in a in your project, senior project, for example, you may encounter such a problem of how to choose a motor, how to interface it, all such the problems may arise. In our kit, everything is okay. I mean, the motor is there, its interface is there. You are just you need to register or configure some pins on the microcontroller to use the motor. But if you are building a motor from scratch, you will need such information. Okay, so let's start by the physics. So let's just skip this. This is just that we're gonna use Ampere's law and Faraday and Maxwell's. Anyways, okay. So if you have a wire like this, okay, and this wire there is a current flowing in that wire, there will be a magnetic field induced. So before if the current is zero, if there is no current, there will be no induced electric field. But once you have a current, you will have electric field like this. I'm sorry, magnetic field like this. Okay. Now, if the current is in the form of a coil, not a straight, okay, we will have the opposite situation. So here, the magnetic field was rounding around the wire, but here it's the opposite. Since the wire is rounded, the magnetic field will be a little bit straightened, okay, inside this coil or this solenoid or whatever, okay. Yeah. Now this is just a motor, so let's examine or illustrate how it's gonna rotate basically. So if you have a wire like this one here, okay, and there is a current flowing in that direction, and there is a magnetic field between this north pole here and this south pole, then you will have a force, and this force will be downward. This force will take, what's the meaning of force? Something that will affect the wire, so it will take it down. Okay, so this part will go down in the direction of the force. On the other hand, the other direction, the other wire, this wire here, this dotted wire, which should be hidden, this wire, the current is flowing in the opposite direction. So the current is flowing in that way. So from here to here, opposite to that current. So the force will be the opposite. The force will be upward. So you have a force on that wire will make it go down. Another force for that wire will make it go up. So what happens is you will have a rotation. Force going down, force going out. So you will have a rotation. And if you have many of these wires, you will have, which is the coil of the motor, you will have a rotation, a big rotation, we can say. So basically, you need a magnetic field, which we call stators. So this part is called stator, and also this is called the stator. And this stator has north pole and south pole. just stator is just, you know, a magnet. Okay. We need also, you know, since this wire is rotating, we need something that just touches the wires. So these brushes here, these two brushes are just touching the wire. So the wire is rotating, and once it reaches this brushes, it will touch the wire. So, and this brushes is providing the current. So they are connected to the source of the electricity, okay, whatever it is, battery or whatever. So whenever a wire touches this brush, a current will flow. Okay, so we need these brushes to provide the current to the touching wires. And if you have such setup, you will have a rotation in that coil here. Okay. Okay, the motor, as I said, just wire. Okay. This wire can be represented in electricity as a model, a circuit model, as a resistor, very small one, a coil, okay, and what we call induced EMF. So if you guys remember from physics, whenever you have a coil and you conduct current in this coil, there will be a reverse induced EMF. Okay, it's just, you know, a voltage that is induced, okay, in opposite to the original voltage applied to the coil. Okay, it's a reverse EMF, reverse to the original direction or the original current. Okay, and this is important in some sense after, you know, that we will see now why it's important. So this is just a practical motor. You have here, you have the stator. The stators are not shown. The stators are the magnetic, which covers the motor. Okay, you have the brushes here. Okay, the commutator is just, you know, many of these coils, you know, and this is actually, you know, the motors that you have in your kit. Okay, just, you know, some summary of what we have taken. What? I'm going up or down? Oh, yes. Okay. Now, how to you know, interface the motor to the microcontroller? Okay. The problem is that this motor needs around, you know, between 0.5 to 1 amperes to run. I mean, you need to provide enough current, very high current, between 0.5 ampere, 500 milliamperes to 1 ampere, so that in this coil, so that it can rotate. Okay, it will have enough force to rotate. The problem is that the microcontroller usually have the maximum current that you can have from the micro is around 20 milliamperes. So this guy can give you only 20 milliamperes, while the motor needs minimum 500 milliamperes. Okay, so it's not possible to run the motor directly from the microcontroller. So if you just connect this the motor directly to the microcontroller, you will just, you know, you provide the current, you put high voltage there on that point, but you will not see any rotation. For that reason, we need something to amplify the current that come out of the microcontroller. And for this, we use one sort of such current amplification is to amplify it using a transistor. Okay. For example, you can use this chip. It's called the TIB120. It's a Darlington pair. If you guys remember analog circuits, I mean, if you don't remember evenly, Darlington pair is just, you know, two transistors connected somehow to each other so that they can amplify more the current. Okay, so for example, if one transistor have amplification of current of 100, so the output current is 100 times the input current, Darlington pair will make it 10,000. Okay, so you can just, you know, draw it as just a simple transistor like this. Okay, so now the input current which comes out of the microcontroller will be amplified here in that, you know, in that branch, which is just the motor. So the motor can be replaced in a circuit using, as I said, a resistor and a coil, and you know, this induced EMF. Okay, and now what is this diode is used for? This diode is actually used such that to reduce the amount of EMF that will be generated when you just switch on or switch off the motor. Okay, so you have here the microcontroller, okay, MSP432, and you need to interface it to the motor. So the motor in a circuit is just, you know, a resistor, a coil, and this EMF. Let's forget about the EMF right now for a moment. And this is not because it's a chip. Anyway, that's fine. You can, yes. So here you have 20 milliamperes maximum. And to have some revolutions, you know, or, you know, to make the motor runs or turns, you need around half amperes to 1 ampere. 500 milli, 1000 milliamperes. While the maximum here is 20. Actually, the maximum, the normal current is 6 milliamperes for that guy. Only 6 milliamperes. But you can do some settings, okay, so that you can have more current on some particular pin. But I didn't cover that yet. So we need some circuit here, some, you know, some module. To convert that small current to large current. For whom of you that, you know, studied analog circuits, if you have a transistor, for example, BJT transistor, or bipolar transistor, you have here a current called the IB, you have here a current called the IC, and the IC is equal to beta IP. If beta is 100, for example, then you could amplify this current by 100 times. So this module is actually can be a transistor circuit. So that's what we're gonna do. We have our microcontroller like this, MSP432, and we're gonna connect its output to a transistor and connect the motor to the collector of this transistor. So here IB, which is very small, and here is IC, which is beta IB. And here is the motor. The motor is, you know, a coil, and just forget about the other components for now. And here is VCC. VCC is just a high voltage battery, like for example 10 volt, for example. In our case, it's 7 volts, but let's just keep it. So this is the motor actually. Okay. And here is a transistor. There is some connection for the transistor. You can combine two transistors together and make something called Darlington pair. Okay. So in the slide that I showed you, he is not using a transistor. He is using this called the Darlington pair. Okay, the Darlington pair is some connection between two transistors that amplifies more the current. That's not our topic now. But if you have to do that yourself, you should buy some some IC that has this Darlington pair. Now, there was there was this guy here. Okay, this diode. And we want to know why he is using this diode. Okay, when you switch on or switch on, let's take a switch off, for example. So when you switch off, this means there was a current, IB. So if we draw the current IB versus time, when we switch off, that means there was a current with some value. Then at some point, it drops to 0. So the voltage of the coil, the EMF that I'm saying, is equal to L, which is the inductance of the coil, di by dt. Guys, when you have a very large, abrupt change like this, from high to low, this here di by dt, theoretically, it's equal to infinity. Very high. Practically, it will be very, very high. 100 volt, for example, something like this. So this 100 volt can crash the transistor. The transistor will just burn. Okay. So we need something to absorb such, such a change. And this actually is, the diode. So this diode here, they will draw right now. Will do that for us. So this guy, to absorb such huge current or voltage when switching on or off. Okay. Because this EMF has a polarity like this. So when you have a polarity like this, this diode will be forward biased. So the current will flow, instead of flowing in that direction here to the transistor, it will flow into the diode. Okay. That's why we need this this diode in here. So let's go back to that guy here. Okay, so this is why we need such diode and such transistor to interface our microcontroller to the motor. Okay, there is a problem though, because this source here, VM, okay, you provide the source to feed the motor. So you want all the voltage to go to the motor. Okay, so if you go here, so this VCC here, part of it will go to the motor between these two terminals, and another part will go to the transistor. To this is called the VCE, the voltage between the collector and the emitter. So VCC is equal to V motor plus VCE. For the Darlington pair, this is around 0.5 volts. So you will lose around 0.5 volt out of your VCC, which is big. Okay, that's why we have another type of connection, which is this one. Okay, so you add another transistor. Now it's not a BJT transistor, it's VDS, it's NMOS transistor. Okay. And now let's now see how this circuit will operate. So if you have high here, then this will work. Okay. And if this will work, all the current will go into the transistor, the BJT transistor, and nothing will go to the VGS, the voltage between the gate and the source of this NMOS transistor. So it will be off. And if this guy is off, then the current, there will be no current flowing in the motor. So the motor will not rotate. So it's opposite to the first circuit. The first circuit, when you have high here, there will be a current in the transistor, so the motor will run. And if you have low, the motor will not run. Now, if you have high, the motor will not run. But if you have low, the transistor will not work. So the current flowing into the transistor will be 0, and all the current will flow to the NMOS transistor that come from the VM, the battery you have. Okay. This guy will work. Usually the voltage here is around 0.1 or 0.2, not 0.5. So most of VM will go to the motor, and the motor will rotate, with higher strength, we can say. Okay. But we have a problem so far with either this circuit or this circuit. We have a problem, is that the motor will run in one direction. So the motor is a very nice circuit. So as a circuit element, if we look at the motor, let's go back here to this slide. So if you have a motor like this, good. If the current flows in some direction, for example, it will rotate like this. So this is one, for example. And if it runs in the opposite direction, so this is called I1, for example. If it runs in the opposite direction, I2, it will rotate in the opposite way. Okay. So this circuit here has only one direction of the current. The current is flowing from VCC or this battery to the transistor. No other direction. The current can't flow in the other way. So we need a more smart circuit from which we can run the motor in two ways. Okay. So let's see how we can do that. We can do that using this bridge here. This is called the bridge. Just to forget about this one. Just look at the one on the right. Okay. So let's see how it works. So let's draw it in the. So let's take this first. This is a snapshot. Okay. And let's go here. If you put 1 in Q1 here for high voltage, let's say high, and high in Q4, and low or 0 on Q3 and Q2, so this guy will be off, this guy will be off, and you will have a current flowing in that direction from the source here. The current will flow in that direction. like this. Then if you do the opposite, if you put 0 here and 0 or low, and you put high here or 1, the current will flow like this. Now look at look at this one and this one. So here the current is flowing in that way in the motor, but here the current is flowing in that way in the motor. So the motor using that bridge can rotate in both ways. But of course you need 2 pins now, not 1 pin from the microcontroller. Okay, one to turn Q1 and Q4 on. At the same time, the other pin will turn Q3 and Q4 off. Then the opposite. So this is actually an IC that you can buy, and you have it in your we have 2 ICs, by the way. We have one embedded on the kit that we're gonna use, and in the package you have another one which is external, okay, that came with the kit, which is external. So you can also make, if for example the one on the board got broken, or which can happen because the motor draws a lot of current, you can design your own circuit using the chips that you have right now as a separate, but of course it will be a separate circuit. Okay, so this is a chip actually that you have on the kit. Okay, so we just need to know or to learn how to configure or put the right voltages or the right outputs to this chip on the board, so that we can run the motor left or right. Okay, and again, these diodes are used for protection, just like the first one. You can just ignore this one, we don't need it. Yeah, here is the chip that I'm talking. It's called DRV8838. So this is the chip that I'm talking about. Nope, my friend. Okay, you have 2 chips, okay, on your kit, one to control the right motor and one to control the left motor. Both of them has this bridge. It's called the H bridge, by the way. Okay, this driver circuit that drives, and at the same time, so it has 2 functions. The first one, it drives the motor. Again, the motor needs a lot of current, and the microcontroller cannot produce a lot of current. So we need this bridge circuit so that we can drive the motor with a lot of current. The second job for this circuit is to turn the motor forward or backward. Okay, 2 ways or 2 directions. And the name of this chip is called DRV8838. Okay. Here is a chip. Let's know what we have in its pins. So you have basically, or you're gonna use basically 3 pins. So just forget about the other pins. Okay, you have a pin called this pin here called phase, which basically determines the phase either forward or backward. So we're gonna use this pin to run the motor forward, so we can move forward or move backward. The second pin is called the enable pin. Forget about its name. This pin in the future, just after 2 or 3 lectures, we will use it to control the speed of the motor. Okay, but now just to put it as 1, and that will make the motor to run at its full speed. And the last bin, you can consider it as, you know, sleep or not sleep, or on or off, something like this. So, and it's a negative logic. So you put one there. If you put one, then this will not make it, this will make it sleep. If you, I'm sorry, if you put one, it will not sleep, or it's on. If you put zero, it will not, it will sleep. Okay, so the IC will be off, so the motor will not run. Okay, so this is a chip that you have on the board. I don't know why it's not working. That's fine. So this is a chip that you have two of them, one to control the left motor and one to control the right motor. So this is, for example, the one that controls the left motor. Okay.
Hey, Professor.
Yes.
Can you go back to, can you please explain pin 6 and 5 again, just briefly?
Yeah, phase BH is
Okay.
it's called the phase bin. Okay.
Okay.
So if you put one, it will go backward. If you put zero, it will go forward. It's negative logic. Okay.
Okay.
So this is the function of of bin 6. Bin 5 is called enable. Okay, just to forget about its name, it's actually used to control the speed. We will see that in 2 lectures or 3 lectures.
Okay.
But for now, if you put one there, the motor will run with its full speed. If you put zero, the motor will not run. So this is how you can understand how it's basically controls the speed. If you put one, it will go to its full speed, so the motor will run, and you know the robot will move with its full speed, highest speed. If you put zero, it will go with its lowest speed, which is zero, so it will not run. Okay. In the future, we will make a kind of combination between 1 and 0, in, you know, in somehow, so that you can go something in between, not the full speed and not 0.
Yeah. Okay.
But for now, it will be 1.
Okay. Thanks, Professor.
Just forget about this. You know. Yeah. Here is the connections that we're gonna, you know, use today. So again, we have two chips. One to control the right motor and one to control the left motor. So this is the left motor, this is the right motor. Okay. And here is the pins that we're gonna use. Okay, this slides actually is used for the same kit, but I think older versions. So that's why there is some typos here. Not typos. Maybe for that kit it was right, but for our kit it's wrong. And this is only just 2 pins, which is these 2 pins in the beginning here. So let's understand this. Let's see, enlarge them. Okay. So first of all, let's forget about these are the direction pins. Okay. So here for the kids that was before, it was port 1. No, now it's port 5. So pin 5.4 in the microcontroller and the pin 5.5 both will control the direction of the motor, either forward or backward. Okay. Pin 5.4 will control the right motor direction. If it's 1, the right motor will move forward or rotate forward. I'm sorry. If it's 1, it will rotate backward. And if it's 0, it will rotate forward. I will show you why it's 1 or 0 forward or backward. Okay, but just, you know, take it like this, like that for that moment. And pin 5.5 in our microcontroller will control the direction of the left wheel or the left motor. Okay, if 5.5 is 0, the left motor will move forward. If it's 1, the motor will move backward. Okay, how is this? Just look at the connections. So this should be 5.4, and it's connected to the phase. As I said to you, phase pin in this driver chip is to control the direction, and the other one is also connected to the phase bin. Okay. Now the speed. The speed is controlled through this enable bin 5 in these chips. So to which bin these bins are connected? They are connected to in two bins in board 2. So bin 2.6 will control the speed of the right motor, and the bin 2.7 will control the speed of the left motor. And as I said, for now, we will just put one there on 2.6 or 2.5 so that the motor will run with its full speed. If we put 0, it will just stop, or the lowest speed, which is 0. And finally, the sleep bins, which are bin 7 in both chips here. These two bins are connected to two bins in port 3, port 3.6 and bin 3.7. Okay, so if we put 0 there, for example, in bin 3.6, this is connected to the right motor sleep. So if you put 0, it will sleep. It will not work. Okay. If you put 1, it will. If you put 1, then you look at the phase and the enable bins, what kind of voltages they have. Okay, so to know if it's going forward or backward, and also the speed. Okay, and this is resumed here in this, summarized here in these two tables. So for example, for the left motor, bin 1.7 is actually bin 5.5. So just, forget this for a moment. It's just 0.5.5. I don't know how to correct it, but anyways. So this should be bin 5.5. So if you have on bin 5, where is the sleep? Yeah. If you have on bin 5.50, and you have for the enable, which is bin 2.7, this one. If you have 0 on the enable, this means the lowest speed or the minimum speed, which is 0, so it will not run. So it's like a stop. Okay, whatever the direction is. But if you have on bin 2.7 1, now the motor can run forward or backward. This will be determined from bin 5.5, not 1.7. So if there is 0, it will move forward. If it's 1, it will move backward. Okay, and the same for the right motor. Okay, this is the most important for our lab. This is the most important slide. Okay, I will just now correct this.
Professor?
Yes.
For the enable, would it still be port 2 for both of them?
Let me correct this for a moment. We can
Okay.
write here. 5.5. Good. Okay. Yeah, what's your question?
For the enable, would it be port 2, or would it change? Because how port 1 changed to port 5.
Okay, for the enable, let's look at here. So this is, for example, B2.6. Let's trace this line, this wire. It's connected to the enable. And 2.7 is also connected to the enable. Okay, this is. Did I understand your question right? Or
yeah, but you know how you're changing port 1 to port 5 for our robots? Is it still the same for our robots with this instruction? Yeah.
No, you should change. So this is wrong. For our robot, it's port 5. Bin 1.6 will be bin 5.4.
But then the other ports, are those correct?
Yeah, these are correct.
Oh, okay.
Yeah,
all right.
Yeah.
Thank you.
It's 5.4. 4. Okay. So good. Yeah, so this is basically what we're gonna do today. We're gonna test. Yeah, this is just a summary. So let's keep this in front of you. All the time. Okay. Okay, so I will share the other screen right now to show you the codes that we're gonna run today. You guys can see my other screen?
Yeah.
Okay. So I just, highlight what's in there for you because it's a lot of coding. So first we're gonna see why these bins in particular. So I think I have the kit here. How could I know which bin is connected to the chips? This is known from the user guide. So look, you can look at this big table here, or for each peripheral you have on the kit, there is a separate, separate a table like this. So these are the bins of the motor. So left motor direction is connected to bin 5.4, not 1.6 or 1.7 like here. Okay. And the right motor direction is bin 5.5. These are the two bins that have, they change it from the versions that this slide is based on. Okay. Enable, which is, this is actually the sleep. So this is, let's call it sleep to make it clear for you. Some problem, I don't know. Okay, so this is the sleep bit. Okay, he called it enable, although the enable should be this one. BWM is the way that we're gonna change the speed. Okay, but he called it the BWM. I will show you in 2 lectures why it's called the BWM. Okay, but it's not so this is not our topic right now. So these are the bins. So as you see, bin 3.7 is the enable, the sleep bin for the left motor. 2.7 is the enable bin. Okay, just forget about this naming here. And again, 2.7 is the one that we're gonna control the speed for the left motor from. And 5.4 is the direction. For the right motor, the direction is 5.5. The enable, or the one that we control the speed, is 2.6, and the sleep is 3.6. Okay, they are summarized here. So let's see what we're gonna do. So we need, so I just copied and paste what we need here. Okay, and let's write this in the sleep signal. And here is enable and parentheses. Okay, so these are the bins that we need. So we need to configure them as a GPIO. So to use these bins, we will send some signals through them. So they are output bins. So we must configure them as GPIO output bins. So these are for the right motor. This is the initialization step. For the right motor, we need 3 bins, 3.6, 2.6, and 5.5. Okay, so set GPIO as output bin port 3, bin 6, this one, which is asleep. Then we put, because we're gonna use the motor, so just put there something so that it will not be in a sleep mode. It will be active. So we put there high. It's a negative logic. If you put 0, it will sleep. If you put 1, it will not sleep. So negative logic. Okay. Now the 2.6 or 5.5 for the direction, 5.4, this is 5.4, and this is 5.5. So the right motor direction is through pin 5.4. So we're gonna set it as output pin. Okay. Then pin 2.6, it will be an output, and through which we're gonna send 1 so that it will run full speed, or 0 to stop it. Okay. And initially we're gonna put 0 there so it will be stop, in a stop mode, which is actually the initial condition. The same for the left motor initialization. Okay, first the sleep pin, it is pin 3.7, and we put 1 there so that it will not be sleep, it will be active. Then we initialize pin 5.5 for the enable, for the direction, and we initialize also pin 2.7 as output, and we put 0 so the motor will be stopped initially. Okay, so the first thing, we initialize the motor, so this function will be executed and the motor will be initialized. Okay, the motor drivers will be initialized. Then in this while loop, what I'm gonna do, I'm gonna go backward first, then stop. So first is the right wheel backward, then stop, then the right wheel forward, then another stop. Then I will do the same for the left motor, left wheel. First I will run it backward, then stop, then forward, then stop. Then I brake here, which is not usual, but just to avoid, because I just want to test if it's going forward or backward, our main configuration is working or not. So I don't want to consume a large power. And by the way, my battery is just drained out from one day of use yesterday. So that's why I put a brake here. Okay. So guys, start writing this code, okay, from the screen. Until because I need to replace the batteries in my robot. Once I replace them, I will test it in front of you. Okay, but just start writing it. So I will put it here in front of you, and you guys start writing or copying this code into your
Professor,
studio. Yes, Clark.
would it be possible to go down real quick just for people to take a screenshot of the main?
Yeah.
Thank you.
You finished?
Yes, thank you.
Okay, go ahead until I try to fix that. Guys, remember if you're gonna buy Energizer, batteries, buy the one that is 1.5. This is 1.2. I don't know if you can see this. This is 1.2. Okay, it works, but some LEDs on the chassis board, not this one, the chassis board itself, will not work. But it will run the motors. Okay. So if you're gonna buy Energizer, look out for this. Buy something that is 1.5, not 1.2, like this one.
Hey, Professor, I just have a question.
Yes.
On line 22 of your code, on the comments, should it be P5.4?
Line what?
Line 22 in the comments.
Oh yeah, because I okay, 5.4. Thank you very much.
Okay, thank you. I
And
just
here
wanted
is
to double check.
5.5. Yeah, this takes me 1 day, by the way, because I trusted this source, this slides, and I was using 1.6 and 1.7, and then it turns out they are the wrong connections. This takes me 1 day. So I'm gonna show you very quick. Okay. Where is right? This is right. Yes. So there is, a kind of paper here. Let me do it in that way. Yeah. Let me do it in that way. So I just stack a piece of paper to the wheels, to both wheels. Okay. You see small paper, this paper and this paper, okay? Just to,
Professor, I think your video screen is frozen.
Yeah.
Your video screen is frozen, Professor.
I don't know.
I
Still
just see a
frozen.
black screen.
The what?
I just see a black screen. That's it.
Okay, let me stop share my screen. Yeah, there is a problem with Skype, with Zoom right now. So I'm gonna show you the, the motor while it's running. Okay. So just okay. First is this is the right wheel. I don't know if you can see it. I'm gonna try. Okay. So look at this, paper here, how it's rotate to know if it's really moving forward or backward. Okay, let me write now. And this guy. I have another idea. Okay. I have this. Okay. Then it will go in the opposite way. Same for this one. Look at the yellow paper. Then the opposite direction again. Okay. So you should have something like this.
Mr. Mustafa,
Yes.
when the wheel moves towards the bumper switches, that's going forward, right?
Towards the bumper, yeah, this is forward.
Okay.
I start backward, then forward for some historical reasons. But you can do the opposite, that's fine. Just copy and paste, switch them.
Right. Okay.
Yeah, and also put something behind. So I put this stuff here, anything you have, put it underneath here, so that there will be space between the wheel and the floor. Okay, so you can have it, running or looping without touching the floor. Okay.